theory of probability. So what we will do today, we will carry on our discussion over the independent random variables. So yesterday, due to some technical reasons, I couldn't complete one example. So we will start with redoing that example. I'll explain it in a bit detail of it, and then I'll discuss the solution to the problem that I posed yesterday. I'll revisit that problem again today, and we'll do some more examples also on independence of the random variables. So what I would like to quickly make you recall is that I'm going to say that two random variables x and y are independent. Okay, I'm going to call those two random variable independent if for any two subsets AB of R, okay, probability that x belongs to A and probability that y belongs to B should be equal to the probability, the product of the probability that x belongs to A times product of the probability that x belongs to what you call B. So you're going to call those two random variables as independent if you take any two subsets. It's actually measurable sets, okay, which I'm not going to get into the detail what do I mean by the measurable sets. So such sets, for such sets, if this inequality holds, in other words, that probability that x belongs to A and y belongs to B is equal to the product of the probabilities, then you're going to call those two random variables as the independent random variables, and this identity should hold for any two subsets of R. One of the consequences of this identity is that if you take the joint CDF of x and y, this CDF can be written as the products of the CDFs of x and what do you call y, and the joint PDF of x and y should be equal to the product of the joint PDFs, the product of the individual PDFs of x and y are the products of the marginal PDFs of x and y actually. So you know, we also yesterday discussed that how using this identity we can drive these two. So what we were doing today, we were discussing an example, and then we had a technical trouble and we need to stop the video. So what I'm going to do today, I'll quickly review that example, and then I'll try to pose a solution to it actually. So what was the problem? The problem was that imagine you have two females, two male and a female, two friends. Okay, imagine this guy is a male and this guy is a female, and then they decide to meet at a park actually, park or maybe some location, okay, between 12 of noon and 1 p.m. okay, between 12 of the noon and 1 p.m. So they decided that we're gonna meet at some time here. Then it was also known that imagine that both of these people arrive at any instant between 12 to 1 p.m. actually. Okay, so their arrival time is any time is any instant between these two. What do you call in this time interval actually? And both of them arrive at the time that are independent to each other. Okay, so if I say let x is the time say in minutes, okay, in minutes past 12, after 12 of the noon, okay, when male arrives, okay, when male arrives in park, and y is the time when female arrives, okay, in the similar time. Okay, so what is given to us is that x and y are both independent actually. Okay, so it is known that they arrive at the independent time t actually, and they arrive. And as we also assume that since x and y arrive at any instant, they can arrive at any minute between in this r, okay, so we can also say that x is uniformly distributed over the period 0 to 60 minutes actually. So in other words, that x can arrive at any time between 0 to 60 minutes, where the 0 represents the 12 of the noon and 60 represents the 1 p.m. actually. And similarly, y also arrive at what? Y is also uniformly distributed between it has also a uniform distribution actually. Okay. Now, if x and y has uniform distribution, then what would be the PDF of uniform distribution? So the fx operated onto x is going to be 1 over 60 minus 0, so it's going to be 1 over 60 when x is between 0 to 60, and it would be equal to 0 otherwise. Okay, so otherwise it would be 0. Similarly, PDF of y is going to be 1 over 60 when y is between 0 to 60 and it's equal to 0 otherwise. Okay, so it's impossible that they arrive at any other time than this 60 minutes period interval. Now, what is also given is that x is independent. Then we can also okay, so what is the key question that we would like to ask actually? The key question that that we would like to answer in this situation is that if one of the males are female, if one person, okay, it could be male or female both, arrives, okay, what is obviously in this time period, what is probability that he or she need to wait for more than 10 minutes for other person to arrive, okay, for other person to reach. So what is the probability that if one of the persons, say male or female, arrives at some instant between this interval, then he or she has to wait for more than, what do you call, 10 minutes for the arrival of the other person actually. Okay, so how you can write it in the terms of mathematics? So for example, if so since this is generic, we're talking about the males and female both, so what you need to do, you have to consider the both situations actually. Now imagine that X arrives at some instant, male arrives at some instant X, the first situation, and Y arrives at an instant Y actually, okay? But this Y, in other words, the time when female arrives is more than X plus 10 minutes actually. So X is the time when male reached, and plus 10, so he waited for 10 minutes. So what is the probability that Y, in other words, the female is going to arrive after this time plus 10 minutes actually, okay, this time plus 10 minutes. So this is about the arrival of the male, and similarly you're going to have, what do you call that, okay, imagine that female arrived first, and she waited for, so similarly you're going to have that, okay, and male arrived at the time, for example, X. What is the probability that that X would be a time, okay, that is greater than Y plus 10, the time that female arrived plus 10 minutes actually. So this is what that we need to compute actually. So obviously in order to compute such probabilities, I mean, one of the things that we can say is that since X and Y are both have the same distribution, both are uniformly distribution, so these two probabilities must be equal actually. In other words, that whatever probability is this, so that, you know, this should be the also same probability actually. So if you compute one, the other would be the same. So due to the symmetry, in other words, this sum of the probabilities is going to be the twice of the one of the probabilities actually. So, okay, one way to do the problem is this, that okay, compute just one of the probability, and then just make twice of it. Other way it could be that okay, compute the both of the probabilities separately, and you will see that the both should be the same, and then substitute it here, take their sum, and you're going to get the total probability of your required, what do you call, situation. Now in order to compute such probability, such a probability obviously can be written as, because this is an event that depends on X and Y both, so we need to compute this probability using, what do you call, the joint PDF of X and Y actually. So imagine I want to compute this, so the probability of X plus 10, for example, less than Y is going to be equal to, what do you call, the integral of the joint PDF of, say, dx dy over some region R actually. So the R is the region that is, say for example, spanned or covered by this inequality. So we will, in a moment we will plot this inequality, and we will see that what would be that region. But there is also another interesting thing is that okay, we also know that since X and Y are independent, so this integral can also be written as the product of fx of x and fy of y dx dy over the R. So since X and Y are independent, so this product can be written as a product, and hence, you know, in order to compute this probability, we need to compute these two integrals actually. So in order to compute these two integrals, we have to take care of, what do you call, two things. Number one, these two things are non-zero in these two intervals, okay, when X is between 0 to 60 and Y is between 0 to 60. So the integrand would only exist if the both of the integral, you know, fx and fy are non-zero, okay, and your X and Y not only should be in, you know, these two intervals, but they should also satisfy this constraint actually. So what I need to do, I need to explicitly plot this R actually. Okay, so the good idea would be to explicitly plot this R. So in order to plot this R, we know that the fx and fy only exist between, they are defined on what do we call 0 to 60 and the interval 0 to 60. So for example, outside that they are not defined. So if I, for example, take each unit as 10, so this is 10, 20, 30, 40, 50, 60, and then you're going to have maybe, I must do, so 10, 20, 30, 40, 40, 50 and 60, and maybe, so they are not really of the same size. Maybe I can rescale them and put them 10, 20, 30, 40, 50, 60 roughly. This is what is going to be the case. So first of all, what do we mean by x between 0 to 60? So in other words, that your one PDF is defined on this domain, which is 0 to 60, while the other is defined on 0 to 60, and obviously, so the both are non-zero. So one is non-zero here, another is non-zero here. So the question is where this product would be non-zero. So this product would be non-zero in this rectangle actually. Okay, in this rectangle, because if you go outside this rectangle, okay, one of the fx and fy must be 0, and hence what do you call the product will be 0. So the both will be non-zero. This product will be non-zero if both fx and fy are non-zero, and they are non-zero in these two domains, which means that they must be non-zero in this rectangle actually. So what is the next thing? The next thing is to plot so in other words, my x and y not only need to satisfy and x and y need to stay in this rectangle, but they also need to satisfy this constraint actually, which is x plus 10 greater than y. So let's compute, for example, what would be the equation of the line x plus 10 equal to y. So if you're going to substitute, say, x equal to 0, so it's going to be x equal to 0, the y would be 10. So if x is 0, y is 10, okay, and if y is 0, x is negative 10, okay, or maybe if y is 10, then x is 0, okay. Okay, so if you take y equal to 0, then x is negative 10, so maybe negative 10 is really here. So this is really what you call the equation of, we should use some other color, equation of the graph of the straight line x plus 10 equal to 1, y. Now which region is the region that denotes okay, so for one thing that is obviously necessary, so this is a bit misleading actually. So it is not necessary that it should pass through 60-60, because 60-60 is not going to satisfy the equation. So that the curve may go like this actually. So it passes through some point, okay, some other point, not this point 60-60, because the 60-60 would not satisfy this. Now we want the inequality x plus 10 less than y. So the question is that, okay, which part of this given region satisfy this inequality? So for example, if I take this, which is 0, 20, okay, if I take, for example, 0, 20, so does 0, 20 satisfy this? So if I substitute x equal to 0 in x plus 10 less than y, and y equal to 20, the inequality is satisfied. But if you, for example, take this point, which is 10, 0, in other words, that I substitute 10 here and 0 here, then 20 is less than 0, it does not make sense. So the region where what do you call, this constraint is satisfied, and the product of these two things is non-zero, is actually this region. So you are talking about this region R. This is the green region, what do you call, R, that you are talking about actually. So what I need to do, in order to explicitly write this inequality, this integral, what I can do is that basically I can now try to write this. So in this region, so since this is in this triangle, fx is going to be 1 over 60 and fy is going to be also 1 over 60, so it's going to be 1 over 360, okay, and then dx dy, okay. Then I need to see that, okay, x varies from where to where actually. I can have this x varies from where to where, so x varies from 0 to this line, for example in this part, but then x varies from 0 to 60. So in other words, in this part x varies from 0 to what do you call this line, and then x varies from 0 to this part actually. So this is, so in other words, you need to split it into the two parts. But you know, another thing that quickly you can do is that instead of considering dx dy, consider say dy dx actually, and put a limit on what do you call y. So what would be the limit on the y actually? The limit on the y, where y starts from this line, okay, and goes up to the 60. So what is the value of the y on this line? So this is equal to x plus 10 equal to y, okay. So what you can do, so you can have the limit 10 plus x, and y goes up to the above line, but the above at the above line, what is the value of the y? So it is 60. While in this entire region, x varies from where to where? So it varies from 0 to 60. So 0 to 60. So this is what is going to be really the integral that you have to solve actually. And then you can see that when you're going to solve this integral, the result is going to be 25 by 72 actually. So this is what the result is going to be. And hence, your required probability due to the symmetry, okay, because when you're going to calculate this quantity, you're going to get the precisely same result, is going to be the 25 by 36. So this sum is going to be 25 by 36. Okay, 25 by 36. You can make this competition. So I have attempted a little bit different than both, but you know, ultimately your result should be the same result actually. Okay. So I hope this makes sense to you. So what was the essence of this problem? That okay, we solved an interesting problem using the independence of two, what do you call, random variables. So now I would like to deal with another problem. And that problem is about also independence. Another example, that example is also about independence, and then we want to carry on our discussion on some new topic actually. Okay, so what is the next question? The next example. The next example that, for example, I'm interested in is example 2b from the book, and that goes like this actually. So suppose that you have a post office, okay? You have a post office, okay? And then if you remember, we talked also about that in a city, if you think about the number of the people, so in a given city or even in a given region or a given market,
there are many people who visit the market actually. Okay, so what is the probability that the person that is going to the market is also going to visit the post office actually? Or the number of people in a day who visit the post office is going to have what distribution? So we talked about it previously that in our one-dimensional discrete cases that we may assume or model it by the Poisson random variable actually. So suppose that the number of people okay, that visit post office is a Poisson random variable, okay, with the parameter lambda. And suppose that there are okay, so the people can be categorized into the the basic two genders, is that either the people are male or the female actually. Now what I would like to do that if we assume that if X is or maybe if we assume that the number of females and the males that visit what do you call the post office in a given day are also Poisson random variable, then these two Poisson random variable must be independent of each other actually. So what is the question or what is the problem that we would like to tackle? That among these people who visit what do you call post office, if we assume that the number of females that visit the post office and the number of males that visit the post office are also what do you call have a Poisson distribution, okay, then these two numbers, these two random quantities should be independent of each other actually. Okay, so the next set of assumption is that if so here's the question. So suppose that each person that visits post office is a male with probability P, okay, and female with probability 1 minus P. Okay, so this is also an assumption that suppose that so each person that enters or that visits the post office is like a Bernoulli trial, so it could be male with a probability P and female with a probability 1 minus P. Okay. Suppose also that if X represents the number of males that visit the post office in a day, in a given day, okay, and Y represents the number of females that visit the post office in given day, and say it is also known that X, the number of males that visit the post office in a given day, also has a Poisson, follow the Poisson distribution, okay, but with the parameter lambda P, and Y also follows the Poisson distribution with the probability 1 minus P lambda. It follows Poisson with the probability 1 minus P lambda, 1 minus P lambda.
Okay.
The key question that we would like to